Welcome to Mobile Coding Academy. Learn principles, build confidence. Let's dive in.
Welcome to today's deep dive. Today we're taking a stack of engineering notes and a very specific pull request scenario to help you build a rock-solid mental model for making concurrent programming decisions.
Right, because our mission here is to figure out how to choose the right synchronization tool without, just blindly memorizing APIs.
Yeah, so picture this. You are reviewing a pull request, and the whole goal is to speed up app performance by loading user profiles concurrently.
Pretty standard scenario,
Totally.
This.
So the code loops through a list of user IDs, it launches a coroutine to fetch each profile, and then it updates the shared UI state. And, it compiles perfectly. It doesn't crash at all.
But it looks a little suspicious, right?
Oh, for sure. It looks perfectly clean.
Yes.
But my instinct when seeing concurrent updates to UI state. Okay, let's unpack this. We need to wrap that update in a Mutex immediately just to be totally safe.
Well, hang on. This raises an important question. What problem are we actually solving?
Well, we're running operations concurrently, right? We have multiple coroutines hitting the exact same state, so we have to prevent a data race.
I totally get that instinct. But concurrency alone does not equal a race condition.
Wait, really?
Yeah, you could have 10,000 coroutines running at the exact same time. And if they are completely independent from each other, absolutely no synchronization is needed.
Oh, right, because the actual trigger we need to be watching out for is shared mutable state, not just concurrent.
Exactly. The shared part is the problem.
I like to think of it like a commercial kitchen. So imagine you have 10 chefs chopping their own vegetables at 10 completely separate stations. That's concurrent, but it's perfectly safe.
Right. Nobody is bumping elbows.
Exactly. It's only when all 10 chefs run over and try to season the exact same pot of soup at the exact same time that you have a total disaster.
That is a perfect analogy. The shared soup pot is where the real danger lies.
Yep.
And in this pull request you're reviewing, the UI state is that soup pot.
Which, brings me right back to my initial reaction. Let's just put a mutex on the soup pot.
Well, you could do that. But a mutex is a really heavy tool.
Heavy how?
People often forget this, but a mutex protects a critical section of code. It doesn't actually protect the data itself. It's essentially an OS-level lock.
Right, so when a thread hits a locked mutex, it just has to suspend entirely.
Yep, it halts. Which is why engineering is really about finding the simplest, correct solution, not just the strongest one.
Okay, so if a mutex is like a heavy bouncer at the kitchen door that halts the whole line just to let one person through, isn't there a lighter way?
There usually is, yeah.
Like, what if we bypass the OS-level bouncer entirely and use something at the hardware level? Like an atomic variable, maybe?
Oh, atomics are fantastic for that exact reason.
Yeah.
They rely on specific low-level CPU hardware instructions, stuff like compare and swap.
So to use the kitchen analogy, an atomic operation is like a chef using a specialized lightning-fast gadget to season the soup in one unbreakable motion.
Exactly. Nobody else can interrupt it, and there's no bouncer required.
But wait, because it relies on a low-level CPU instruction, it's highly constrained, right?
Yes, very.
So atomics are really meant for tiny things, primitives, simple counters, Boolean flags, things like that.
Yeah, you can't easily wrap a complex, deeply nested state object in a simple atomic reference.
Right, because our PR is dealing with a complex UI state object, and atomic is just too small for that.
Exactly. It won't handle complex concurrent mutations cleanly at all.
So we're kind of boxed in here. A mutex is too heavy for our UI state, and an atomic is too small to handle a complex object.
It feels that way, right?
Yeah, so do we have to write some kind of custom synchronization logic for this PR?
Actually, no. What's fascinating here is that modern declarative frameworks often solve this middle ground for you completely.
Oh, really? How so?
Well, if that UI state is backed by something like StateFlow, calling StateFlow.update actually handles the concurrent mutations safely under the hood.
Hold on. So by just using StateFlow.update, we're essentially getting thread-safe atomic updates for free, like without ever explicitly writing a lock.
Precisely. It uses really efficient synchronization internally.
Wow.
Yeah. So it ensures that if multiple coroutines try to update the state at the exact same millisecond, absolutely none of the updates get lost.
So for UI state, it completely removes the need to introduce a heavy mutex into your application logic. That drastically cleans up the mental model for me.
It really does. It means you don't just throw locks at the wall to see what sticks.
Right. We verify if we actually have shared mutable state first. And then we pick the simplest tool for the architecture. So StateFlow.update for declarative UI state, atomics for tiny hardware level counters, or a mutex for complex multi-step critical sections of code.
Couldn't have said it better myself.
Awesome. Well, to wrap up this deep dive, I want to leave you with a final thought to mull over.
I love these.
Since we established today that a mutex protects a critical section of code and not the data itself, what happens to your app's safety if another part of your codebase modifies that exact same data without using your carefully placed mutex? Keep that in mind next time you're reviewing a pull request.
Thanks for learning with Mobile Coding Academy. See you in the next deep dive.